Welcome back to Physics in Minutes. Today, we're going to look at constant acceleration physics problems, which are also 1D kinematic equations. I'm going to explain how they work, and we're going to look at the equations like this. While they may look complicated right now, hopefully by the end of this video, you'll understand better how to use them and where they come from. So before we get into problems with kinematics, let's just look at the basics of velocity and acceleration. Assuming there is no acceleration, velocity is just v equals d divided by t. That's something that you may have heard of before. Maybe you've heard about it in its other weird form where it's a dirt, d equals rt, and that's distance is equal to rate times time. I don't like this one as much, so we'll kind of stick with this. Again, that just means velocity is the distance traveled divided by the time it's taken to get that far. And velocity is something that we probably inherently understand, just having been in cars our entire lives, basically. Acceleration is a little bit more complicated, and that is the rate of change of velocity. That just means that when you're accelerating, your velocity is going to be changing, and acceleration measures how fast it's changing. To kind of understand that, just think about when you're driving in a car. If you put more pressure on the gas or you put pressure on the brake, your velocity is changing, so you're applying some acceleration there. One last thing I want to point out, and I cannot emphasize enough before we actually go on to these problems, and that is that you need to be in SI units. This is really, really important. SI units are meters, seconds, and some combination thereof. If you're not in SI units and you go through the entire problem, you may have trouble converting at the end depending on how savvy you are with conversions. So it's better to just start at the beginning and make sure that everything has units of meters and seconds. Trust me on this one, you'll thank me later. So now let's look at the actual kinematic equations. And you can see here that there are quite a lot of them. I'm going to explain briefly what everything means, and then we'll just jump into problems. So first, the ones that I've chosen to use, they can be exchanged for 1 or 2D. Ignore this x comma y here, that's kind of irrelevant. And every time you see a little x next to a value, you can ignore that as well. That just means the x component, but that could also be changed for y, which again, you can ignore until we get to 2 dimensions. What I do want to point out though, this is important, is you will see every now and then there's a little 0 next to a few of these numbers. So here we have a v0, there we have an x0. That just means the initial value of velocity or position, respectively. And the way you refer to that is v0 or x0. And again, it just means the initial values. Sometimes they're written as vi and xi, which generally makes a bit more sense because it's initial, but we're just going to stick with what I have here. If it does not have that naught, for example, we have a v here, we have an x here, that means the final value. So v and x are just the final value of your velocity and your position. Once again, sometimes they're written as vf and xf for final, which does make sense as well, but that's just not what I have here. One last thing I want to point out, the x is not distance, x is position. So we have an x and an x naught. That means the final value of x and the initial value of x. If you want to find the distance traveled, what you have to do is take their difference. So the total distance traveled is your final value of x minus your initial value of x. That right there is d. And that's really important. Don't confuse d, distance traveled, with x, which is position. Let's do a simple example with a bike that starts at rest and has some acceleration a. Let's suppose that bike travels a total distance of d. So it starts from here, goes over there, and that's a distance d. The question is, how long did it take the bike to travel that distance? What some people do is at this point, they just look at the equations, they try and pick one that looks like it might work, and then go with it and see what happens. But that's really not the best way to do it. What you should do instead is write down the things that you have on one side and write down the thing or things that you need on the other. Doing this will make it much clearer which equation to choose. So we know, for example, that we need time. And that's just because the problem says, how long will it take? That's obviously asking for some form of time. Now what do we have? Well, we have acceleration, that's clear. As I mentioned earlier, d is not position. D is the distance traveled, which, again, like I said, d is equivalent to x minus x naught. So we have x and x naught combined in d, so that's pretty useful. There is one more thing we have that I haven't written down, and that's when I said the bike starts at rest. That is a phrase that they love to use in physics courses, starting at rest. What that means is that your initial velocity is 0. If anything is at rest, it is not moving at that instant, meaning its velocity has to be 0. So even though that wasn't written, it wasn't explicit, that was part of the problem. Now that that is all written down, what we do from here is look at the equations and find out which one has all the things that we have, but also has the thing we need. If it has something we do not have, then we're not using that equation. For example, if you look at this one right here, it has x and x naught, which looks good. It also has v naught in time, which is good, but it has right here that pesky v final. We don't know what that is. We have no idea. So this equation is not the way to go. You need to have only what you have and what you need. So if you keep looking, you'll eventually find the equation we want is this guy. Because again, it has a, x, x naught, and v naught, as well as t, so that is the one to go for. Now that we've chosen the equation, the rest from here is just algebra. So let me just write down really quickly. We have x equals x naught plus v naught t plus 1/2 at squared. And I know my handwriting is not the best, so I have the equation down here you can look at as well. All we have to do is plug in the values we already have. And it's pretty much already done for us. V naught, for example, do you remember what we said that was? If it starts at rest, that's 0, so this entire part goes away, which is pretty nice. We also have d, which is not included anywhere, but if we take this x naught and we move it to the other side using subtraction, what we end up with is x minus x naught on that side, which is the equivalent of d. So the left-hand side is just d, and the right-hand side is simply going to be 1/2 at squared. Now all we have to do is solve for time. So let's divide a to the one side. So we have d divided by a equals 1/2 t squared. And then we have to get rid of this 1/2. So let's multiply by 2 on every side. So we get 2d divided by a equals t squared. The last step we have to do is notice that we have a t squared and not a t. So you need to square root everything. If we do that, we end up with 2d over a square rooted equals t. And right there, we have solved our first kinematic problem. At this point, you would just plug in the numbers that you're given. I didn't do that because it makes a lot more sense to have things symbolically like this when I'm writing in such a small space. Now let's check out one more problem really quick. So let's say we have this house and it's a height h. And in this house lives some kid who is a bit of a brat, and he likes to climb up onto the roof and throw his football straight down to the ground. The question here is, how fast is the ball going when it hits the ground? So once again, the first thing we do, we divide it up, we write out what we have, and then what we need. What we need is fairly obvious. The velocity of the ball at the end. So we need v. And I'm realizing that I should have labeled right here, this v should be a v naught, because that's the initial value. We need the final value of velocity. What we have is v naught and h. Those are pretty explicit. And once again, h is the same as d in the previous problem, where it's the difference between x and x naught. So once again, both of those kind of come along for the ride. There is one more thing we have, and I didn't even say it, I didn't allude to it, but it's there. And that is acceleration. And we know what acceleration is because we're only dealing with things that go up and down. In that case, acceleration is just due to gravity. Gravity is pulling the ball down towards the earth, and so acceleration is automatically g. Or depending on how you define it, it's going to be negative value. Once we have all of those things combined, all we have to do is look at the equations, and once again, we look for the things that we have, the things we need, and find the perfect equation. We do not have anything to do with time. That's one thing you should be quick to notice, which means that any equation with time in it at all is going to be irrelevant to us. And that basically leaves us only with this one right here. So that's the equation we're going to use. Let's solve this problem. Fortunately, this problem is already basically solved algebraically for what we want, because we want v. That's it. All we have to do is plug in the values of the other things that we have. Now, there is one trick here. So I'm going to say that v squared is equal to v naught squared plus 2a times x minus x naught, just what the equation is. We already said that h is going to be the difference between x and x naught. So we can write that this will be related to h. But there is one problem here. The final value of position x is located down here. The initial position is up here. What that means is the ball is losing height, which makes sense because he's throwing it straight down. But that means that x minus x naught is not actually h. Instead, it has to be negative h. And this is really important because, again, the ball starts here, it goes downward, so it's losing height. This term becomes a negative h, which is okay. It's fine to have a negative h. We also already said that a is negative g, and that's because gravity is a negative in that it brings things down towards the Earth. If you set up your coordinate system like normal, where up is positive, down is negative, g is always going to be negative. So with that knowledge, we can say that v, and if we square root everything, is equal to v naught squared minus 2g, because the g is a negative, times a minus h. Let me just clear things up a little bit. So this may look complicated, but fortunately, two negatives, we have one here, we have one here, end up being a positive. What that means is we can just get rid of that and make this a positive right there. Because we had a negative g and a negative h, they cancel out and just leave a positive number. Once again, at this point, you would plug in the numbers and get your answer. We don't have any real numbers, symbolically just makes more sense for me here. And that's it. The important part here is that if you're dealing in the y direction, meaning throwing a ball up or down or any object really, gravity is going to be your acceleration and it's going to be a negative value. Don't forget that. And that is it for constant acceleration physics problems or 1D kinematics. If you have any comments or questions, let me know down in the comment section below. Be sure to like and subscribe if you appreciate this content. And I hope that I can see you next time where we're going to be dealing with 2D kinematics where things get a little bit more complicated. But don't worry, we'll work on it together. See you then.